Hello, my name is Kyle, and for the last 6 months or so, I've been working on building a rockfall simulation using a game engine. The idea here is to work towards developing a tool that can be used to examine how those rockfalls and their fragmentation might impact various areas of interest in your infrastructure. In this presentation, I'll basically go through the work I've done thus far, covering where the project is now and how we got there. So let's get cracking. Before getting too into the weeds of what I've been doing in detail, I want to take a second to cover game engines themselves in case any of you are unfamiliar. Game engines are collections of tools and an environment that facilitates the creation of video games, and act sort of like an engine does in a car to make the game run. Here's a quick look at what Unity looks like. This is the engine that I've been using for this project. It's probably a little familiar if you've used tools for digital art or 3D modeling before. Game engines let you create objects, build a world around them, define interactions between objects and that world, etc. The obvious question is probably why are we using a tool that makes video games for this kind of simulation? But it turns out that game engines have a lot of features that are more broadly useful beyond just making games for entertainment. The big ones for our purposes are supporting realistic environments for the simulations. A built-in physics engine lets you handle physics interactions out of the box. Simple to implement camera controls that allow you to manipulate the perspective or field of view easily. And tools to make intuitive interfaces that are easy for users to learn and to interact with. So this covers why we're using a game engine, but what exactly are we using it for? Well, like I mentioned at the beginning, we're building a rockfall simulation application. If any of you are familiar with Matt Anderson or Zach Sala's work from a few years back, this is largely extending their work using some new tools and techniques. So I started off with a very simplified model that fragmented cubes, and have ended up with a model that pseudo-randomly fragments rocks in response to collision at runtime. And I'll cover what those terms mean in detail later on if you're unfamiliar. The rest of my presentation will cover how I went from point A to point B, with a couple of side tangents, and talk about how these work and what they're doing in more detail. I'd also like to note that because I'm showing almost all of this through video recordings, and I'm not exactly sure how smooth they'll be in a remote presentation like this, if anything's jittery or anything, I apologize, but feel free to contact me after the presentation, and I'm happy to pass along any footage directly. So how do we get to the current model? This is a brief overview of the key points along the way. While deciding on our programming approach, I implemented block fragmentation using a fixed pre-computed pattern. After choosing an approach, I added terrain for blocks to collide with, and switched to a new fragmentation method using a third-party Unity add-on called Rayfire, which allows for significantly more control over how the fragmentation is carried out. I'll talk about what that means when we get there. Lastly, I developed a very short workflow to make good-looking rocks quickly, largely for demonstration purposes in talks like this. Starting at the beginning, the first order of business was to investigate the merits of Unity's new data-oriented programming approach, which you can see on full display on the left. Quick technical details. Classically, Unity uses object-oriented programming, storing data in game objects that have scripts attached to them to manipulate their behavior. Data-oriented programming favors strongly segregating data from the systems that operate on that data, and is very much in the beta testing stages for Unity integration. You can see the major perk of the data-oriented approach here, in that on the high-end machines, it has a significantly higher performance ceiling when handling lots of individual moving objects, the cubes in this case. However, in spite of a performance gain in these instances, we actually decided on the conventional game object approach instead for a couple of reasons. The first of these is that the game object system gets to use Unity's standard physics engine, while the data-oriented approach does not. As we can see in the cube tower here, we get a nice tipping motion and then fragmentation behavior that looks reasonably legitimate. In this case, like I said, we're using a pre-computed fragmentation pattern, so everything will fragment the same way. But each of these blocks gets swapped out, it maintains its velocity, it falls according to gravity, and it collides with one another and with the floor, as expected. For physics purposes, however, like I said, the data-oriented approach is very much still in beta. And what this means is that you get really strange behavior like the low friction sliding going on in the stack here. It has a difficult time transferring a block's position to a new block. So when we go to fragment our cubes in this case, it resets all of the orientations to be the same, which you can see right there. And this is not ideal. This is going to take a significant amount of work to fix and make behave more normally, which you get for free using the standard objects. However, there are also further problems with this method in that it is in beta and the physics engine in general is a little bit weird. So this is just spawning in a tower of cubes and they spontaneously start sliding and falling down all by themselves without any outside forces whatsoever. So this is not the sort of physics engine that we were hoping to build off of, and it's largely for these reasons and the lack of resources and documentation for how to use this method that we ended up going with the more standard object-oriented approach instead. So now that we had an approach in mind, I started work on getting terrain into the simulation. This terrain chunk is taken from near the Grand Canyon that I just found online, and it works quite nicely as a placeholder to have something resembling real terrain in the simulation rather than just the flat plains that we had in the previous demos. And here you can see that quite happily the simulation will handle even reasonably large numbers of objects moving around independently without any performance dips, which is nice. So now that we've got terrain in and cubes in and the basic style of fragmentation, and we've decided on an approach, how did we start moving towards our current model from these models? The first order of business was to get better fragmentation going. So when I say we had pre-computed fragmentation working before this stage, what I mean is that I took a cube in Blender, which is just a 3D modeling software, and I manually planned out how that cube would fragment. And I took that fragmented version of the cube, and anytime I would try to fragment a cube, I would swap the unfragmented cube for the fragmented cube that I had built by hand. And that's obviously fine for testing a proof of concept, but it's not great when you're interested in dynamic fragmentation in response to physics, right? So that's what this model tried to address. There's an asset called Rayfire, which is conventionally used in Unity for achieving this kind of fragmentation. So we thought to try it out, and it works great. So this is a model showing pseudo-random runtime fragmentation. What do those two terms mean? So pseudo-random fragmentation means that the fragmentation pattern is random, but that randomness is based on some seeded pattern. So if I'm interested in recreating a particular style of fragmentation, I just note the seed that gave me the fragmentation that I liked, and I can reuse it again later. Or, which I'm doing here, I can randomize the seed for each fragmentation instance so that they all behave differently based on a series of parameters that I've input, which is really nice. The second part, the runtime, that means that these fragmentations are not computed at all before the simulation is being run. When I drop a cube like this and it hits the platform like that, it decides in the moment how it's going to fragment in response to that collision. So you get nice, dynamic, more accurate looking fragmentation patterns, which is nice. So now that we have good fragmentation, we need to dress it up a little bit and put it in a somewhat more realistic terrain environment, and then try to refine it down a little bit better. So the next step involved that little tangent I talked about earlier. We wanted to be able to switch the cubes out for realistic looking rocks, both for better demonstration purposes and so that we could get a more intuitive sense visually of how the fragmentation was behaving. So I took some time and figured out a workflow for procedurally generating reasonably good looking rocks using Blender. In this case, what I mean by procedural is that I can give it a series of inputs and another pseudo-random seed to design the base model for a rock, and then the rest of the workflow is built around texturing it and getting it in such a way that Unity can use the rock model in our simulations easily, rather than having super high polygon, high fidelity looking rocks, which are really nice to look at. That's what I'm showing on the slide here. But their geometry is a little bit too complicated for easy fragmentation. These rocks that you're seeing are about 1 million polygons, that's individual faces making them up. And for Rayfire to happily fragment a rock, it wants to be beneath about 256 polygons. So here is the 256 polygon version, seen from a number of different angles. Still looks pretty good. You can obviously see some of the blockiness of the rock block up close, some of the sharper lines, but it still looks good enough. The shape is all right for the use of our demonstrations, at least. So let's have a look at some of those demonstrations. This first one is just to showcase the runtime fragmentation I talked about earlier, being computed in response to each rock's collisions. I redid the terrain model for these demos. This is the next item we're going to be replacing, which I'll talk about in a couple of slides. But we can see the rocks are fragmenting on their way down the slope as intended. This is a nice close-up of that pseudo-random fragmentation I mentioned earlier, shown both with rocks and cubes because visually the fragmentation pattern differences are quite difficult to see in the rocks at this scale and much easier with the cubes. This is a new feature for this demo. where we are supporting fragmentation of fragments. So you can see, we'll go in for a close-up here. Not only does the rock fragment, but its fragments will also fragment into subfragments, and those can fragment into further subfragments. You can control the depth value, it's called, for this, for how many layers do you want the rabbit hole to go down, and performance obviously takes a hit as you go higher and higher. But just getting some base level of can we fragment our fragments, that's now happily working. And the last feature for this model is arbitrary damage thresholds. So setting some predefined value before runtime starts, we can chuck rocks off of the cliff, and if they exceed a damage threshold, as then they've had enough impacts that they've taken enough damage that they should fragment, then they'll fragment. And if they don't take enough damage to exceed that arbitrary threshold, then they won't fragment, as we can see the one making its way down on the left-hand side there. So now that we've covered the full current model with runtime pseudorandom fragmentation, fragmentation of fragments, and damage thresholds, I'm going to briefly talk about where we'd like to go next before wrapping up. The next major milestone for the application itself is to get real terrain data into the app and working. The placeholder we've been using for now is just stuff I've made quickly in Blender to make the current slopes. We'd really like to get actual road cuts or any slopes of interest to our users into the simulation so we can start dropping rocks down that instead and start to calibrate against something resembling a real model. The other thing that's app related is to work on what's called a minimum viable product, which is essentially the fewest number of functional features you need to start putting your application into the hands of potential testers, so you can start getting feedback to guide the further development of the app. To facilitate that, we need a user interface, which are basically going to be some buttons for people to hit to be able to control the application, rather than just using the Unity editor, which is only set up for me for experimentation for now. It's too complicated otherwise. Broader goals are to explore and implement better fragmentation models. The big two factors for that right now are to incorporate known patterns for things like joints, other features that might be present in a rock mass that can be collected in field data. We'd like to be able to incorporate those into the fragmentation model. Furthering that, though, we'd really like to develop a relationship between the sorts of data that get collected in the field and the input parameters to our fragmentation model. Things like how difficult it is for a rock to break, things like that. In doing that investigation, we're also quite likely to explore a few other procedural fragmentation options aside from just using Rayfire. As much like you saw earlier in this presentation with the comparison between the two different programming approaches, just picking the first thing that you find does not necessarily lend itself to having the best results. So although our current fragmentation method we're pretty happy with, moving towards solving these other problems, we're likely to investigate using a few other options like Houdini, which is conventionally used for procedural special effects, and other tools like it in the future, before we decide on one to use for certain. And that's my presentation. A huge thanks to Gene and my other supervisor, Rob Harrop, who isn't here today, for putting up with me and offering lots of guidance throughout the process, and to the several different groups that listed on the screen for help funding the research and providing data for me to use. I'm happy to take questions for a couple of minutes.